Okay, now let's just discuss about the item number 3 here, okay, which is using the Matlab to apply a pre-trained CNN, or we call also, this is also known as transfer learning. So what we do is that we want to develop our CNN using by modifying the well-established CNN architectures. So in this case, or in this syllabus, we only focus on LXNet. So how actually can we modify the LXNet so it can solve our problems? Okay, this is the one that's related to your mini projects. Okay, your mini project, you need to use this one. Okay, among again, like I said before, among these four, number 3 is the best way, or the best way in, and the practical way, or the common way to develop the CNN, because there's a lot of advantage in using approach number 3, because in approach number 3 you don't have to do some, when you train from scratch, you need a big data. But of course, when you use that is very difficult for you to access if you don't have any very big data. So that's why people like to use number 3, because number 3 is like you are borrowing other people's brain to solve your own problem. So of course you don't need empty brain. Okay, you already have your brain already have, you just imagine the terminology is like you have one brain which is already have a capability to learn something which is bigger, and you want that brain to solve your small problem. So that's means when you apply this number 3, so the training in training process, the convergent process is going faster than you are training from scratch, because you're using the brain which is already learn many things, big things. Okay, and another terminology for this transfer learning, or the number 3 approach here, the approach number 3 here is also known as transfer learning, is that just imagine is like this is the, okay, before that I want to say that this is one of the specialty about CNN as compared to shallow neural network, because before this, when we talk about the shallow neural network, or before we talk about deep learning, it's very rare to see people import other network to solve their own problem. But the specialty about CNN, you can do that. This is what we call as transfer learning. Okay, so it's like the terminology is like you have a friend who, for example, you have a friend is good at score in for example O level. I'm sorry, let's say your friend gets straight A for A level, for example, and meanings that this your friend is very good at solving all the problem in exam, and then you are preparing yourself to answer O level question, like let's say mathematics question in O level. So it's like, okay, you can say to your friend, can I borrow your brains? I want to solve. I want to borrow your brains for me to take the O level exam. Of course, you can score after that. So that is some kind of terminology how actually a transfer learning looks like. Of course, in reality, you cannot do that. You cannot, you cannot borrow your friend brain. Of course, it's it's not biologically, it's not easy to to change the brain. Okay, but in CNN you can do that, meaning that well established CNN architecture like LXNet, GoogleNet, you can use it to solve your small application. Why I said your application is very small is because, again, if you read the history of LXNet, like we explained before, LXNet have been trained to the training process itself takes 6 million image to classify 1000 classes, meaning among these 6 million image, AlexNet capable to classify into 1000 classes. So imagine that you want to use this one for your small set of image, later you will capture using you selfie yourself wearing mask and not wearing mask, and then you want AlexNet to classify into two classes only, which is either wearing a mask or is not wearing the mask. So you have two classes, but in reality AlexNet managed to to classify 1000 classes among 6 million image. So imagine that. Of course, that's why I said that we can, instead of we try to to find out what is the best architectures to solve our problem, so it's better for us to borrow other people's well-established architecture, and it's a learnable, it's a trainable, it's a learned architecture. It's already learned with 1000 classes, so it for sure it can solve this. Only it is just to classify into two classes. It's not problem for them. Okay, so doesn't matter is it AlexNet, GoogleNet and so on, but in this case we only focus on AlexNet. So something that is related to item number or approach number 3 here, you can go to your Matlab and you can open the file CNN transfer learning. Okay, this is the same. This one is the same thing. What I do is that I just take this example from the Matlab website. So you just search AlexNet Matlab AlexNet transfer learning or Matlab transfer learning AlexNet. Then you find out there's a one example which is exactly almost similar with this one. Okay, but I just modified a little bit. I want, because if you apply the Matlab, it will open the data set which is in zip version. You need to unzip first, but I already unzip and I put it here, which is merge data set and merge data. So merge data, if you double click again, it is similar to digit data set. If you double click the merge data set, you have a picture of image. This time is a color image. Okay, it's not a grayscale. And then we have several classes here. 1, 2, 3, 4, 5. We have 5 classes of image. So you want to train the AlexNet to be given the image, it can classify the image into these 5 classes. Is it a cap? Is it a cube? Just Matlab put there Matlab in front to, it's just for the marketing purpose, I think. So actually this one is cap, this is a cube, this is a playing card, this is a screwdriver. So you just double click, you can see the image there. Okay, so so how do we do the transfer learning? How do actually we want to modify the AlexNet to solve our problem, or in other words, make AlexNet to be customized to solve our problem? Okay, again, the first step is similar to the previous one. Okay, of course you need to assign your data with your image data store variables there, IMDS. And again, the setting is similar because the arrangement is similar. Because we have 5 classes, so every image which is represent the cap, you put under the folder cap. So the same things, you need to arrange in that way. Then you put, okay, if you execute this section, you will get the IMDS there. Oops, sorry. I have a wrong directories there. Okay, run section there, because I set the current folder. Okay, that's good. So you can see here, this is my IMDS. Okay, you can see the labels there. We have a cap, okay, Matlab cap, Matlab cube, Matlab playing card and screwdriver. So even this data set is very small. Okay, one classes you have only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's just 11 or 12 image per classes. So it's very small. So it's not enough to learn to make a deep learning or CNN, because CNN need very big data to to converge. So that's why this approach is applicable or is practical, is suitable where actually you don't need a very big data, because we believe that once you get the LXnet is already at the almost global minimum point. Okay, so that's why if you do a pre-train like this, it will go to the global minimum faster. Okay, because you start at the point where you are almost close to the global minimum. So that's why we do that. And then we don't need more data, because the starting point is almost close to the global minimum. Okay, in training progress there, just imagine that. Okay, and then we will need to split our data there. Again, this is a very biased way to do, because you only split in two data. One is training data, one is validation. Okay, if you compare this one between this one and the previous one, is almost similar. Just this one we mentioned the number of data, but at this point you can also give the ratio. So means that this function split each label can support two mode. One, you can mention the size of the data here, or if you don't mention the size, you can also mention the ratio like this, 0.7, meaning that 70% will go to training, and the another 30% you can go to here. Okay, so just proceed with this things first. Okay, we proceed. Okay, split it into here. Okay, this is your, now the IMDS split into 70% here, 30% here, and then this one is just to see the information about our data. Okay, we run section, this section, then it will display here. Okay, you can see that we only have 15 image per classes. 15 belong to cap, 15 belong to cube, 15 to playing card, and so on. And then this one, so again this one is for display purpose like the previous one. We just want to randomly selected any image inside this data set, and we just display a sample of it. Okay, so this is a sample of image there. You can see that it's a color image. It can be a cube, it can be a cap, it can be a torchlight, and it can also be a playing card like this one. Okay, and then you just select define your net as LXnet, because LXnet is already built-in inside the built-in function or built-in library, Matlab built-in library. So if you write LXnet, you will get the net which is belong to LXnet. Okay, and then once you assign your net equal to LXnet, which is a trainable LXnet or well-established LXnet, a trained LXnet, I mean, so then you can display the architecture of your net, meaning that now you are displaying the architecture of LXnet. Okay, by applying by executing this one. Okay, now let's say we execute that one, and this one is just to see the size of the first layer. Of course, the first layer is the input layer. It should be a color image 224 times 224. That is the LXnet already fixed the input size with 224 times 224 times 3, which is color image, and the size of x and y is 224 and 224. So meaning that if you have any image which is in different size, then you need to resize the image according to 224 times 224 before you can fit into this LXnet. Okay, just go to this slide. Okay, let me just remind you on the LXnet architectures. We go back to the slide. Yep. Oh, it's a 227. Sorry, it's not 224, it's a 227. Okay, this is LXnet 227, so it's exactly like the one here, 227 times 227 times 3. Okay, maybe in this example it's not LXnet, I changed it to LXnet. It might be this one is GoogleNet, so I changed it into 227 times 227 times 3 in the comments there. Okay, So because might be previously this example is using Google Nets. Okay, Google Net have different size input. So then you need to change according to the what type of well established architect or CNN architecture that you are using. Okay, if you are using LXNet, you must make sure that the input image has been resized into 227 times 227. So again, this one is just to, if you put net.layer 1, is just, it will give you description about layer 1, which is the input layer, where the input size is 227 times 227 times 2. Okay, so and then yep, that's so this is if you want to get the input size, then the input size is net dot layer number 1 and input size. So then you get the input size, because if you call input size, because net here dot here, this is the member variable of this net, so then you get the size here. So it's just a get input size. So the input size variable now assigned as the size of the input size of this LXNet. Okay, so after that, so how to modify this LXNet to solve your problem? Because now our problem, we have this small image which is belong to 5 classes only. And again, if you talk about the LXNet, it can be classified into 1000, but now you want to classify it into 5 classes only. So if you go into this slide back, so you realize that each CNN, normally, like I said before, when you do some tasks, let's say you want to solve some problem where you want to classify into 5, then the output there, the last output should be the size of neuron should be 5. So same go to the LXNet, because LXNet have been trained with 6 million image to classify 1000 classes. So that's why the output neuron here is 1000. So now from these architectures, the one that you need to modify is this one, the last layer. Okay, because the last layer now, let's say if you want to solve a problem of image to be classified into 5 classes, then this 1000 need to be converted into 5 neuron only instead of 1000. Okay, so that's why you can see here, once we manage to assign our net as LXNet, we need to modify at this section. Okay, replace a final layer. So meaning that you just copy. Okay, now you assign transfer layer. Transfer layer is you copy from net of layer 1 up until the third last layer, you assign here. Meaning that from this net, you are removing the last 3 layer. Okay, you just copy paste here, but you remove the last 3 layer. So why we need to delete the last 3 layer and assign it here? Okay, once you assign this one, let's say I execute this one, then you need to create the new architectures where you copy this LXNet layer from 1 to the one that before the last 3 layer, because you already removed the last 3 layer here. Okay, you only take the fourth last, okay, not the third last, the fourth last layer, from layer first until the fourth last layer is inside this transfer layer. So you copy here and then you create your new 3 layer. So that's why you remove this 3 layer of the LXNet, because you want to replace with your own layer, which is will make your last layer only have 2 neuron. Okay, again, why I said a 2 neuron. Remember that these 3, like I discussed in the previous Matlab code, if the fully connected is belong to the last layer, it will attach with the soft layer and classification layer. That is for sure. Okay, so this is actually is the last layer. Even you have 3 line, this is the last layer. Okay, remember this one, the one that we do from scratch. Okay, I said before, this is your last layer, and when you draw the layers there in with Word document there. Yep. So again, this one is the previous one. It's not the, okay, you see that this is create simple deep learning from scratch .m. Okay, we have discussed this before. When you have arrived at the last layer, normally this fully connected layer is belong to the softmax. So that's why I put it as a softmax of 10 neuron, meaning that this architecture only actually is classify the image into 10 classes. Okay, into 10 classes, like I said before. So again, same as this one. So why we need to remove the last 3 layer? Because that last 3 layer is represent the last layer. Okay, so that's why I said in this slide before, when you want to modify your LXNet architectures, the one that you need to remove is this one. Instead of 1000, you need to change it into 5 neuron only, or 5 classes only. But and this one is in Matlab code is represented by, this one is represented by this 3 line, or this 3 line, same like this one. This 3 line is represented by this the last layer here. So that's why we need to remove 3 layer in this one, because this last 3 layer represent the last layer. So that's why we just copy the whole LXNet except the last layer, and the last layer you need to add it with your own customized classes, which is 5 classes, because the number of classes here you get from here. Actually, number of classes is here, this one you will get 5. Okay, this is how you do automatically to get your classes. Of course, you can just write num classes equal to 5 is also can, but of course we instead of manually set that, you need to, one way to do is we can obtain the number of classes according to the data set we have. Maybe later, if you want to apply the same code for other application or other data set which is not the number of classes is not 5, then you don't have to set back this one, because this one already automatically automatically get the number of classes from the data set that you want to process. Okay, just the number of classes is equal to 5. So that's why this number of classes we put here. So that's why you fully connected, you will get fully connected layer 5 here. Okay, this is 5. So that's the okay, that's it. Meaning that very simple, right? Just you remove the last 3 layers, which is represent the last layer of your LXNet, and then you added your own last three layer, which is represent the last layer of your problem, because you want the last layer to have 2 classes only. So if I run this section, now you have a customized, so you can see here number of classes equal to 5. So that's why now it's not 1000 anymore. The last layer you have a 5 neuron only. And then okay, this one is the process of you want to resize your image, because the image that you in the data set is not 227 times 227. One way you can do is you can do this thing, because this actually, when you apply this thing, it will make sure during the training process automatically any image which is not 227 times 227, it will resize during the training process. Okay, so this is the set, you set that, but it's not resized yet. It will resize when you apply the training at the bottoms there. Okay, this one is just the function of how actually it will, when you write this instruction, it will automatically, when the training process read the image from the dataset, it will automatically apply the IM resize, and then the size is according to 227 times 227. Okay, but actually I'm not suggested you to, you can try this one if, let's say, in your assignment it's very heavy for your Matlab to classify or to proceed with the training. Then we need to do this externally, because I also have one project, a previous final year project, which is very difficult to run the code when you are resizing during the training. So what I do, that I give you some other code, which is we need to resize it externally. Means that you open the image, you resize, and you save back to another folder. Then when I want to proceed this program, then I use the one that I already resized the image from the externally. So but this one you do internally, means that during the training it will resize. Okay, so let's do it internally. Okay, now we proceed this one, we proceed this one. Okay, again this one we already discussed about this one. Now we're using a maximum epoch is 6, and then we set our mini batch size equal to 10, and then we have a validation data. Let's execute that one. Now we train our network. Okay, you can see that we train our network, but this layer now have a LXNet, modified LXNet. It's not from scratch. Of course, it's a little bit faster to train, and it's appropriate to use a small training data, because it's already, the W that fixed here is already at the position where the point is close to the global minimum. So that's why it's very fast as compared to you training from scratch. And then you put the training data. Okay, now let's execute that one. Okay, now the training is started. Okay, so let's already start there. As you can see, it's almost 100%. That is training accuracy, but you can see that the validation accuracy is finalized at 90%. So meaning that this is quite challenging data as compared to the previous one. Okay, because training is achieved 100, but the validation is only stable at 90%. Okay, but because I already set the maximum epoch there is what? Maximum is 6 epoch, so that's why we stop at 6 there. Yep, 6. Okay, then the less you can just again calculate according to the previous lectures. Okay, the validation accuracy is 90%, and then of course if you want to execute this section, you just show the train. If you want to execute this section, you just it's just showing you the modified LXNet that you do. Okay, I skip this one. Okay, again this is for testing, but of course again it's not this is a biased way to do, because you do testing with validation data. So again, let's say if you want to make it better, then make sure that you modify this code and change it into the one that I have teach you in the previous lecture. Means that you need to separate your validation into testing data. Then at this part you must put the IMDS test to find the score, that to classify, to see whether your programs there is correct or not. Okay, to find the accuracy here, must make sure that this one change into IMDS test, this one this is also IMDS test. Okay, but this one I'm sure that the accuracy is 90% because you can see over here the accuracy is 90%, so it's not represent the performance of the system. Okay, because normally testing is the data that don't involve in training process. Validation data is the data involved in training process but don't involve in updating the W, while the training data itself involved in training process as well as involved in updating your W. So that is the difference between training data, validation data, and testing data. Okay, if I run this one, then that is the some random example we capture from here, and that is the label or the output of the output of the CNN that you have already modified from the LXNet. Okay, it's a correct playing card. This one is it a screwdriver? This one, I think this one is wrong. This one is correct. This one is torchlight. This is the cube. Okay, let's we run another one. Hopefully they capture another sample, random sample. Okay, cap correct, playing card correct. This is torchlight correct. This one is torchlight correct. Okay, so how about another trial? Okay, so I think this one is torchlight. It's not a screwdriver. Yep, this is where it's wrong. So that's why the accuracy only 90%. How many classes? Oh, sorry. Screwdriver, torchlight. I think the cube, cap, playing card. So I think this one is torch. Okay, this one should be torch. Yeah, it's a screwdriver. Yeah, it's a screwdriver. Okay, but of course the accuracy is only 90%, meaning that there's a 10% errors there. Okay, so in your assignment, please make sure don't do something like this, meaning that later you need to, in order for you to show the performance of your CNN, then you need to implement it by using testing data, IMDS test. Okay, then you need to modify this code a little bit so you can do that for your assignment. Don't show the performance in terms of accuracy while you calculate the accuracy based on the validation data. Okay,